Well, hello everyone, and welcome back to Adrian's Digital Basement. Have you ever wondered what would happen if you took an IBM PC and you ran it at the same clock speed as an Apple II, 1.024 megahertz? No, you never wondered that? Well, it's something that I have wondered for a long time. And it's always been conventional wisdom that the 6502 used in all sorts of 8-bit computers in the 80s was much more efficient than Intel's processors used on the IBM PC. So if we took an IBM PC and we ran it at that 1.024 megahertz like an Apple II, would this actually be usable at all, or would it be completely useless? So in this video, I want to figure that out. So without further ado, let's get right to it. For this video, I decided not to use an Intel 8088 to run it at 1 megahertz to compare it to the 6502, and that's for a very specific reason. The main difference is this processor can address up to 1 megabyte of RAM, while the 6502 can only address 64K. Because of the larger address space on the 8088, Intel needed to multiplex the address lines and the data bus lines together. There just weren't enough pins on this package. So that means anytime the 8088 is accessing the RAM or the ROM, which is all the time, that's while it's running program code, there are actually 2 or more cycles that have to pass just to do one memory access because of that multiplexing. That's not a problem on the 6502, and is one of the reasons why the clock speed isn't really comparable between the Intel 8088 and the 6502, because the 6502, without multiplexing those address and data lines, can access the RAM and the ROMs and any other part of the system a lot more quickly and more efficiently. To make matters worse, the Intel 8088 is also a 16-bit processor internally, but it has an 8-bit external data bus. So that means that read and writes to the RAM are actually 2 read and writes because it needs to work with 16-bit chunks, but it only has 8 external data bits, which means it's even slower. Now, the original 8086 processor, which looks the same, 40-pin package, has an external 16-bit data bus. That means it can access the RAM a bit more efficiently, but it still has to do the multiplexing between the address and data lines. So while the XT's motherboard clock speed is 4.77 megahertz, there are so many bottlenecks in and out of the 8088 that if I ran it at 1 megahertz, it would be way, way slower than the 6502. And that brings us to the other motherboard here, which I showed in the intro. This is that 286 motherboard I recently worked on that has SIM sockets on now that I replaced the SIP sockets. If you haven't seen the video on this, I'll link in the description below to that. This processor is 16 bits, just like the 8088 and the 8086, but it does not multiplex the address lines or data bus lines. There are enough pins on this socket to go directly to all the RAM and the ROM on the board, and you don't have any of the slowdown from that multiplexing. There's another benefit on the 286 versus 8088, and it's that the number of clocks required for every instruction to complete is probably faster on this chip than it was with the 8088. In modern parlance, the efficiency of the chip is called instructions per clock, but I think it's more clocks per instruction with these older chips because, at least with the 8088, like on the XT motherboard here, there are some instructions, as far as I'm aware, that can take up to like 30 clock cycles to execute. It's really, really slow, and I think things sped up a little bit with this chip. But the 6502 compared to the 8088 is so much more efficient in that regard as well. Now, the architecture on the Intel processors is way more complex than on the 6502. I wouldn't call the 6502 a RISC chip, but compared to these chips, it is so much less complex. Intel just kept throwing features at these, and even with the 286 here, they added a ton more instructions to the Intel architecture that just extended the functionality, but made the complexity of the chip, well, that much more. Now, it goes without saying, it's not an apples-to-apples comparison comparing a 6502 to a 286. This processor is 7 years newer and probably costs a fortune compared to the 6502 for the actual chip. Not to mention, the motherboard design is going to be a lot complicated because there's so many more address lines and data bus lines on this chip versus on the 6502. Now, I have to throw a caveat out there that this isn't going to be a super scientific video where I custom write some very similar assembly language code benchmarks that could run on the 6502 Apple II and on the IBM PC, and we could then time those loops to see how comparable they are. Unfortunately, I don't have enough assembly language chops to be able to do something like that, especially on both of these platforms. That would be pretty cool to do, so if anyone wants to try to write some super similar code, I could always try to do a follow-up video where we compare the two platforms and we actually time these loops. I intend to run this at 1 megahertz and then boot into DOS and then run some old software and games on it to see if the system is even usable at 1 megahertz, or was the software that was written for it so inefficient, or the processor so inefficient, that at 1 megahertz it results in a completely unusable system. Now, I have a feeling that if IBM ever released a 286 system or a PCAT that ran at just 1 megahertz, I have a feeling that the assembly language code, like the games and software that would have run on it, would have had to been written a little more efficiently, a little more cleverly to result in good performance. And I feel that that was something that developers on the Apple II, and let's just pick up the Apple IIc here, had to do, because the original Apple II, designed in 1977, was a TTL machine, and it had a bunch of funny things about it. Like the video memory wasn't linear, so you had to use clever programming to draw stuff onto the screen and make that work. And over the years, Apple II developers got super clever to be able to get good performance out of the 1 megahertz system. Now, the BBC Micro, as an example, was running at 2 megahertz, and you had a lot more horsepower available, double. Not to mention, its video subsystem didn't have idiosyncrasies like the Apple II did, so programmers didn't quite have to be as clever. But when you compare the performance of games on the BBC versus the Apple II, even though you have twice as much horsepower available on the BBC, it's not like most of the games on the BBC are twice as fast or have much smoother graphics on the Apple II. I think back in the 70s and 80s, machines had such technical limitations that you had to design your programs around, that programmers got really good and clever at working around those limitations. And there's no denying the fact that a 4.77 megahertz PC is a pretty slow machine as well, and some of the games that ran on this thing were somewhat impressive when it came to the performance they would give. But since the performance target on the PC was 4.77 megahertz, and you had potentially 640K available of program memory versus 64, I don't think you had to be quite as clever with your software development as you did on those other systems. Now, if you were a software developer back in the old days developing software for the XT, or of course all the 8-bit competitors, I'd love to hear more about it, because I might be completely off base with all of this, and I'd love to hear from someone who actually knows. Now, when it comes to the PC architecture, there's something about it that makes it especially well suited to this underclocking exercise we're about to do here. And it's specifically the video subsystem on the PC. Well, it's run by external video cards, and those cards, whether it's CGA, monochrome, or VGA like this one, are not really reliant on the clock speed on the motherboard for generating a video signal. On most, if not all, other home computers that were released in the 70s and 80s, ones that had a video display output on them, the video circuitry was tied into the timing circuitry that ran the CPU. And that includes the Amiga, the Macintosh, the Apple II, Atari 8-bit line of computers, the Commodore stuff, I think the BBC Micro, although I'm not totally sure on that one. And that means on those systems, if you try to change the clock speed of the motherboard, which would alter the clock speed of the CPU, it would affect the video output and would render it, well, unusable. When you had a CPU accelerator on one of those machines, it didn't change the clock speed of the motherboard at all. And what had to happen is you would plug in a card or a little module with the new CPU on it, and it would have some glue logic and its own crystal oscillator and clock circuitry. And what would happen with the CPU is it could execute instructions faster, more quickly that is, but most of the time, whenever it needed to talk to anything on the motherboard, any of the peripherals on the motherboard, it would have to downclock to the original stock clock speed, because all of those chips were designed to communicate to the CPU at the original speed. And that meant if you took an Apple II and you ran it at 2 megahertz with an accelerator versus 1 megahertz, you didn't get totally double the speed. And that's because the accelerator kept having to slow down to 1 megahertz whenever it was talking to stuff on the motherboard, and then it could speed up and run some instructions at a faster speed. And even then, most of the time, if you were only using the RAM on the motherboard, the CPU would also have to slow down to talk to that RAM. And that's why a lot of accelerators have either cache memory on them or their own memory, because then the CPU could talk to its own memory at a faster speed and only need to slow down if it's talking to the memory on the motherboard. Compare that to the 5150, where video cards plugged into the ISA bus. It didn't matter what was going on the motherboard. The video card could generate its own video output because it had its own clock circuitry on it. And the only thing that mattered was the CPU could read and write the memory on the video card across the ISA bus and control the registers on the video chip, so it could set up the video signal and stuff like that. And on the original IBM PC, the ISA bus was synchronized to the clock speed, so 4.77 megahertz. So theoretically, when you overclock the system, say to 8 megahertz, if you have a Turbo XT, I guess it runs the ISA bus at 8 megahertz. I'm not actually totally sure about that. I've never looked at that. On the original 5170, which was the first 286 machine that IBM released, the ISA bus was still synchronized to the clock speed of the CPU, so 6 or 8 megahertz. And that's why 8 megahertz as the ISA bus standard was sort of established, because that was the fastest 286 that IBM ever made. Now, it was up to the clone manufacturers in the aftermarket to make PC motherboards that were faster than IBM's motherboard, and they ran into an issue that the ISA bus at that 8 megahertz standard, well, if you tried to run it at 12 megahertz, a lot of cards couldn't go that fast. So what chipset manufacturers did, like this chips technology chipset on here, is they implemented a clock divider for the ISA bus, which is controllable, so you can control the division of the clock speed. So when this thing is running at 12 megahertz, the ISA bus is actually running at 6 megahertz. This allows all ISA cards to be able to communicate with the CPU, which is running at that faster speed, so you're not going to run into issues there. But of course, with the ISA bus running at half the clock speed of the CPU, that means the CPU needs to wait whenever it's talking to the ISA bus, and that's what you've heard of as wait states. Now, those can be introduced in accessing the RAM as well for a similar reason, that at 12 megahertz, it's possible the RAM is not fast enough to talk to the CPU, which means the chipset is able to signal the processor and tell it to halt, or hold on a second, while the memory is getting ready with its data and to put onto the data bus or the ISA cards, and then the processor waits a little bit and then comes back and says, let me grab the data off the data bus, okay, we're good, and it keeps on executing. This is not that different than the bottlenecks on the 8088 with its multiplex data bus and its 8-bit data bus that cause it to slow down quite a bit accessing any part of the motherboard. Now, I picked this motherboard as a candidate for this video specifically for a couple of reasons. It allows me to enable 0 wait states for the RAM. So that means as we slow down the processor down to 1 megahertz, we can set it to 0 wait states, which means the processor can access the RAM at full speed at all time. It never has to slow down and wait because of a performance bottleneck. In addition, there's an ISA clock speed divider in the BIOS that I can control. That means I can either have the ISA bus divided by 2, so like the stock configuration with this running at 12 megahertz, this runs at 6, I can actually turn that off where the ISA bus is running at the same speed as the CPU, which running at 12 megahertz would be too fast. It means most of your cards wouldn't work. But if we slow this down to 1 megahertz, we want the ISA bus to be running synchronous to the CPU so we don't have any additional wait states. Now, this 286 motherboard has another potential slowdown that other 286 motherboards won't necessarily have. Remember I talked about the fact that this is a full 16-bit processor. That means it has 16 data bits that go to the RAM and the ISA and stuff like that. Well, notice there's only one BIOS chip on here, and this is an 8-bit chip. Unlike the ISA and the RAM, which you notice we have two 8-bit SIMs on here, the processor would have to do 2 reads from the ROM anytime it was accessing it. So that means anytime something uses a BIOS routine, which DOS uses a lot, that we're gonna have a slowdown. Now what this motherboard can do, and this is a facility of the chipset, not typical for 286s, is it can do something called BIOS shadowing. And that means there's a routine and some capabilities inside the BIOS that allow the code in the BIOS to copy itself from this 8-bit wide ROM chip into DRAM. And then it's able to write protect what it's copied, and that becomes the ROM. So anytime a BIOS routine is called, instead of it going to this chip here, it goes into the full speed 0 wait state RAM. That completely removes the bottleneck of this being an 8-bit chip on a 16-bit system. But there's actually another bottleneck that could have come into play if it wasn't for the BIOS shadowing. EPROMs like the one used on this board are quite slow. I wouldn't be surprised if this is a 200 nanosecond chip, which means that if the processor were running at 12 megahertz, that's just far too slow. So there would need to be wait states introduced. So anytime accesses are happening from the BIOS, additional wait states would have to be inserted, potentially 2, 3 wait states. And that's a completely separate issue from the 8 16-bit thing I talked about a moment ago. And with this BIOS wait state thing, there's really no way to control what those are. There's no option in the BIOS to turn that off. But luckily that shadowing, that copying of the code from this also speeds that up because the RAM doesn't have any wait states. So once we copy it into the RAM, we're going at full speed. Now, if the motherboard were designed with 1 megahertz in mind, like the Commodore 64 or the Apple II, a 200 nanosecond ROM chip is totally fine. The cycle time at 1 megahertz, no issues. It's really because the PC was designed to run at a faster speed that the designers had to implement wait states in talking to these slow ROM chips, at least on faster motherboards like this. So with all that said, that's why I picked this 286 motherboard. 0 wait states on the RAM and on the ROM because it's shadowing, and I can run the ISA bus at a synchronous speed to the CPU, which means when this is running at 1 megahertz, I can give this every possible advantage there is to be as comparable to something like the Apple II. Okay, enough talking. Let's get this thing hooked up to the bench and see if I can even run this thing at 1 megahertz so we can do some of these experiments. There's actually one more thing about the architecture of the IBM PC that makes it really well suited to this underclocking or overclocking exercise. And it's that compared to something like the Apple II, the chipset on the IBM PC actually has hardware-based timers on it, which allows software to create timing loops across different motherboards, even running at different clock speeds. The Apple II, on the other hand, has no way to create timing loops that are not connected to the clock speed of the CPU. So if you ever use an Apple II with an accelerator in it, you'll notice that games always run way too fast, and even things like sounds coming out of the beep speaker are going to be at the wrong frequency, because even the timing loops for the beeping is created with CPU instructions. On the PC, on the other hand, it is a programmable interval timer, which is part of the chipset, which does the beep speaker. That means that even when you overclock your CPU or underclock it, your sound coming out of the beep speaker will still be the same frequency. Now, I hear people yelling at their screen right now saying, on the original PC, there are games that don't work well when you have faster CPUs. And yes, that is the case with early games, but I'm pretty sure what happened with those is that the developers probably ported the game from another system like the Apple II, and they just used CPU timing loops like the Apple II uses, and they didn't use the programmable interval timers. Since at the time, all PCs that were available were simply running at 4.77 megahertz, they didn't really take that into account. But I know for a fact there are plenty of early games that use the interval timers, and that means those run fine on systems that are faster. Now, sometimes they still have issues with systems that are super fast due to other CPU loop considerations, but anything that uses the interval timers should probably work fine, even underclocked down to 1 megahertz. Now, as I populate this motherboard with the various components, there is something else to consider. It is possible that some of the cards that I'm plugging into the system won't work properly at 1 megahertz because the ISA bus will be running at 1 megahertz, and I'm sure when this stuff was designed and tested, well, it was never tested to run at such slow speeds. 4.77 megahertz, yes, it would have been tested for that, although on 16-bit cards like this video card, I don't even know if that would have ever been tested that slow. Probably 6 megahertz is the minimum. I'm not anticipating that anything is going to come up with the cards. Probably all going to work fine. I think we might have one issue on this motherboard, which actually crept up a little bit when I was testing this motherboard in the last video on it, where I was changing out the SIM sockets. In that video, I was replacing the crystal oscillator, trying to see different speeds this motherboard would run at, and I seemed to have run into an issue when the clock speed was too low going into the chipset. It seemed the keyboard stopped working. Now, this is the keyboard controller right here, and this is actually a microcontroller. It's based on the 8042 or the 8051, which is an Intel microcontroller series, and it's possible that these chips don't run properly at super slow clock speeds, because I think there are like digital analog converters and various logic bits in there, and maybe they were just never tested to run at such slow speeds. And I seem to recall, like I said, when I popped in a slower crystal here, the keyboard just stopped working. Now, with everything here is plugged in and ready to go, I even have this large speaker here so we can hear the sound. You might be wondering, how am I going to do this underclocking? Now, I did relocate the crystal oscillator from over here on the motherboard to right there, which will allow me to easily swap out different crystals. And I happen to have a little assortment of them in this box here. This one being the original 24 megahertz crystal, which is on the board, and I actually have more of these. And you know, you can just swap these in at will to try to change the clock speed of the system. Originally 24 megahertz resulted in 12 megahertz CPU, but this thing seems to run perfectly at 28 point whatever megahertz this is, and that gives you around 14 megahertz. Any faster than around this 28 megahertz seemed to introduce issues into the chipset itself, which is already being overclocked. This is only rated for 12.5 megahertz, and it's running at around 14. Now it's this divided by 2. Now, since these only come in finite values, and I don't have an unlimited supply of these at every possible value, we're gonna have to use something else so we can try to find the upper and lower limits of what this motherboard can do. And this is what I'm going to be using to do this experiment. So if I flip this on, this is a frequency generator or a frequency synthesizer. It's a very inexpensive one. It can generate sine waves up to 30 megahertz. So it's not very high bandwidth. I kind of wish I had bought a higher bandwidth one now at the time. And sorry about all the dust that's on the screen. It has dual outputs with BNC jacks, and all we need to do to connect and run this motherboard is to pull this out and use something like this that goes from BNC, and I'm going to be using these clip leads here, and they just have little pins stuck into the ends here, and we'll connect that right up to the motherboard. And I happen to know with these crystal oscillators, where this is pin 1 here with the square corner, that represents this corner right here. Ground is that pin, and the signal input is that pin. We need to inject the signal plus ground from the frequency generator, and we should be able to run this motherboard. So frequency generator is connected. If we run this at 24 megahertz, there we go. It's going to output 24 megahertz when I turn on channel 1 here. The VGA card is connected to the capture device. So if we turn on the output of this, power on the motherboard, we should theoretically get output. There we go. We have a working system. Trying to get everything in shot. This is as wide angle as I can go. So if we push F1 to continue, the system should boot. If we run speed 600, the landmark speed test, this will just quickly give us information. And you know what? I'm going to unplug the speaker for now so we don't have to listen to it beeping away. 12.038 megahertz. We're getting 18.5 megahertz effective speed. And that's because this is a zero weight state motherboard for the RAM and everything else. And on the original PC-AT, the 5170, there were weight states for the memory because it was using very slow memory. So even at 6 or 8 megahertz, it wasn't fast enough. So in this landmark test, if the system were running at 6 megahertz, we'd get an effective speed on the CPU graph around 6 megahertz or 8 or 12, depending on your clock speed. So the 18 there is an effect of the zero weight statesness of this motherboard. Now what's cool about this frequency generator is we can change the speed on the fly, and watch this. So I'm on 24, now it's 23, 22, and I just keep going down. You can just see the clock speed drop. And if we hit F9 for a retest, you'll see that the CPU speed is now 9 megahertz and it's currently at 18. So divided by 2, it's exactly what we expect. And we can keep getting slower and slower, and the system is running without any issues. Let's hit F9. Keyboard is still working as well, so the keyboard controller is not having an issue at the moment. So we're running at 6.5 megahertz, which, yeah, we're at 13 on the frequency generator. We're at 12, 11, 10. Now 10 megahertz, I hit F9. Nothing's happening. Oh, it worked that time. But I think the keyboard is starting to act up and it will not be working reliably. So 4.997 megahertz. And again, it's able to determine the clock frequency of the CPU using those interval timers, because altering the clock input here does not change the clock to the interval timers. Those are derived from this 14.3 megahertz crystal that's on the motherboard right here, completely separate from this one, which is used for clocking everything else. Now let's try to escape out of this here. Boy, I really cannot. Pushing escape key doesn't really do anything. Seems like none of the keys are really working now. So I think we've sort of reached the lower limit of the keyboard controller on here. Let's ramp the speed back up. Let's see if the keyboard starts working again. Nope, still not working. So I think it crashed the microcontroller that's in the keyboard controller. Time to power cycle the computer. Looks like it went to BIOS defaults here. We're going to go to the setup. The keyboard's not working because we're running at an appropriate clock speed. And I'm just going to hit F10. It's kind of cool. This has a recovery mode, very much like new modern BIOSes. If you create a scenario where your system doesn't post, it will actually revert back to the defaults on the second reboot. This BIOS from 1989 might be the first example of that system default because the system didn't post. I'm not quite sure. What we can do here is I can start typing on the keyboard, and let's start dialing down the clock speed here until it stops working, just so we can see exactly where we have a problem. Oh, there we go. 10 megahertz, stopped working at 10 megahertz. That means the CPU is currently running at 5 megahertz. We are unfortunately pretty far away from the 1 megahertz target that I want to get to. I happen to have had plenty of bad motherboards come through the basement, ones that were so damaged they couldn't be fixed. And what I always did is, if it had a keyboard BIOS on there, I took it off the board and stuck it on here. Now I might even have more of these floating around, but I happen to have these 4 chips that I just had in stock. Now, as far as I'm aware, all of these are pretty much intercompatible with each other. So all of these should work on this motherboard here. And this one says Megatrends, but kind of has the Intel logo, so that goes back to the fact that this was originally an Intel microcontroller. And this one here, oh, there it says 8042, so that's the microcontroller itself. And this one says Phoenix. So this was designed by AMI. Phoenix, I don't know if there's anything different about it. We have a Jet Key 3.0, the fastest keyboard BIOS around, and one here that just says AMI. And the one that's actually on here now, if we move this over, is an NEC part. It says 8042 again, and it looks like it's from 1990, 51st week. So I just set this back to 16 megahertz, and yeah, we haven't got our typing back. Let's swap out this chip here for one of those Intel chips and see if they're a little bit more forgiving with the clock speed. There it is in there. It's running at 16 megahertz, so we shouldn't have any issue. I've noticed that if the clock speed is too low, we will get a keyboard error in the BIOS here, and we can't actually boot the system. So we'll know right away if things are screwed up. Okay, so it passed the keyboard test. Therefore, we should be able to boot to DOS without an issue. Okay, so let's start ramping down the speed. Let's see when this stops working. Oh, it stopped working there. And we're at 11 megahertz. And I think I went 2 notches there. So it might have stopped at 12 or 11 megahertz. The Intel one is even worse than the original one that was in there from NEC. So out with this chip, and let's try a different one. Let's go to this JetKey one here. I don't know who makes this, who is JetKey, but let's give this a try. Frequency generators at 15 megahertz, so we should be good to go. Even while these other two chips we tested will work at 15. All right, here we go. Let's start ramping this down. Oh, we're less than 10 megahertz and it's still working. Ah, okay. We ran into an issue at 7 megahertz. Can't type anymore. Let's just make sure I didn't have a dodgy connection though. I'm gonna leave this at 7 megahertz and we'll power the thing back on. We'll look for that keyboard error that might pop up if there really is a problem. Okay, so we're not even posting now, so I have a feeling we have an issue. Oh, yeah, we did post. Oh, it's just really slow. Okay. Originally, I had this motherboard with 8 megabytes of RAM, but I took it all out knowing that the RAM test would slow down if we're ever running it at 1 megahertz. Control-Alt-S for the BIOS. Oops. Oh, it's still working. So this is still set for 7 and it's still working. So I don't know why it crashed switching down, but maybe I had a dodgy connection here. Anyhow, the reason why I went down to 2 megabytes is I had a feeling that counting up 8 megabytes at 1 megahertz would take very long time. And I don't think with this BIOS there's a way to skip it. System is booting. So we are currently running at 3.5 megahertz. Let's turn this down. Okay, we're still working. It's at 6, 5, 4, 3, and by the way, 3 on the frequency generator is divided by 2. So the CPU is currently running at 1.5 megahertz. So we are really close to my 1 megahertz target here, and the keyboard still freaking works. And now this is set for 2 megahertz. Yes. So let's go to here and run speed 600. I just want to make sure that everything is working, like with the compact flash card that's on there is working, and it's able to detect the CPU speed correctly, and everything is good. You can see how slow things look. It has really, really slowed down. Wow. Now keep in mind, all of this stuff here on the motherboard is running at 0 wait states, including the video card I'm using. This is a Cirrus Logic card. I forgot which model it is, but even it runs at 0 wait states. So we are running as fast as possible when it comes to the wait states. And of course, we're running at such a slow CPU speed that any wait states would really impact our performance. 0.998 megahertz. Check that out. Now I want to get this clock speed dialed into the exact same speed as the Apple II, which happens to be 1.024 megahertz. And what I can do is I can just type values in here. So I'm just going to poke around on here until I can figure out the exact speed. And there we have it, 1.024 megahertz, and we're working. Now there's one more thing we have to consider here just to make sure we're getting as much possible performance at this slow speed as possible. Originally this motherboard was configured for 14 point whatever megahertz, and that meant the ISA bus was divided by 2, running at like 7 point something. Well, that means that currently we're running the CPU at 1 megahertz, and that means the ISA bus is running at half that speed, so around 500 kilohertz. That is way slower than it needs to run. Let's try to fix that. One thing we can see on this benchmark here is the video speed is running at 251 characters per milliseconds, which is bytes per milliseconds. I have the original 28 megahertz crystal back in the system. So we have the system currently running at 14.213 megahertz, which gives us the effective CPU speed of 21.93, and the video speed is 4509.36. In this MIPS benchmark, we're getting an overall score of 2.0, and we are 8.68 times faster than the original IBM PC XT. I'm just writing these down. And here in Check It, we're getting 3584 dry stones and 68.7K wet stones. Now, there's no reason to believe that all of this stuff wouldn't just scale linearly when we divide the clock speed down to 1 megahertz. Everything should be 1/14th the speed of this. There are two things that actually might change, and it's the video speed and the hard drive speed. And that's because those go through the ISA bus, and as soon as I slow down the CPU and then I take away that divider for the ISA bus speed, we're not going to have a 1/14th speed for the ISA bus, because we're going to be going from 7 point something megahertz all the way down just to 1 megahertz. So it should be about 1/7 the speed. Although the CPU plays a part in accessing the video memory and the hard drive and stuff like that, and the CPU will be a lot slower. So it will be more than 1/7 slower, but I don't think it's going to be 1/14th slower. Here in the video speed, we're getting 7165 characters per second through the BIOS calls. And of course, BIOS calls are very slow and inefficient, but writing directly to the video memory, we're getting 44.8K per second, or characters per second. And finally, we have the hard drive speed utility here from Core International. I'm just going to write down what this is. 1943.1 K per second. Incidentally, I tried to use the frequency generator at 28 megahertz to run this instead of this crystal, and I couldn't get the motherboard to even post at all. I have a feeling my shady wiring here is not really good enough. I need some coax cable that went almost to here and then broke out to little pins. Then it would probably work without issue. Now, one thing we haven't looked at is the BIOS bus speed. We need to look at that on an oscilloscope because we're just taking for granted what it's actually running at. The BIOS has an option for proc clock, which I think is this crystal oscillator divided by 4, and the other option is divided by 2. Now, I have this card right here, and this is like a little prototype card, and I have an oscilloscope probe connected to the clock pin and the ground pin here. And with this, we can just pop this into the motherboard like so, and then we can bust out the old Zoe here, and we should be able to look at the actual clock speed of the ISA bus. Now let's power on the system. I have frequency displayed there. If we power this on, there we go. What are we getting? Around 7 megahertz, which is exactly what we thought we'd be getting. And that's with the original 28 megahertz crystal oscillator in there. Okay, so with the system booted up, obviously we haven't changed anything. It's completely working. I'm gonna reboot this thing and let's go change the divider from that /4. If we get into the BIOS here, where's that divider? Here it is, bus clock source, proc clocks divided by 4, so that's the crystal oscillator divided by 4. If we change this divided by 2, and we reboot the system, we should take a look at what happens here on the ISA bus. Ah, yes, oh, it's trying to work. Look at that, the video card looks kind of screwy. 14.2 megahertz, so indeed it is running at the full speed of the CPU now. And it says we have an issue of some kind, so let's hit F1. Ah, look at that. It's hard to read, but there's like garbage on the compact flash card. I think it's just running too fast for the ISA card. So yeah, the system is kind of working. And that's of course because the ISA bus speed being too fast is not affecting anything on the motherboard. The motherboard, CPU, RAM, all that stuff, still running at the same speed, but the video card is having an issue. So I'm going to feed 12 megahertz into the system, 12 megahertz, and we need to turn on the output. There it is. And that means that the system should post because now the ISA bus should be running at 6 megahertz along with the CPU running at 6 megahertz. And that is well within the spec of all of this stuff. And here's the Zoe, and you can see ISA bus is now running at 6 megahertz. So switching that particular setting in the BIOS from /4 to /2 absolutely runs the ISA bus synchronous to the CPU speed. So I'll just leave this here. Hopefully that's readable. It's probably a little bit blurry, but the system is fully working. So what we need to do now is I need to carefully move this, and we're going to lower this thing down to that 2.053 megahertz. After changing the interval, the ISA bus is now running at 1.02 megahertz. Awesome, and the system is still running. And I want to see if the video speed has sped up, but not from when I ran it at 14 megahertz, but when I ran it at 1 megahertz, but with the ISA bus set to /4, which meant it was running at like 500 kilohertz. I wrote down the bytes per millisecond, and it was 251, and look, we are getting 503. So indeed, the video speed is twice as fast. Now the ISA bus is not underclocked versus the CPU speed, which is frankly more comparable to the way the Apple II works, because the Apple II and Commodore and all these other systems, the video is displayed out of the main memory. So the CPU can write to the RAM on the Apple II at the full CPU speed, and then in the other half of the clock cycle on the 6502, that's when the video circuitry is drawing what's in RAM to the screen. So it means the Apple II video subsystem really does run at 0 wait states at the full CPU clock speed, which is basically kind of what's going on here. It's obviously a little bit more complicated because we have a VGA chipset and stuff in between, but this VGA chipset seems to be very efficient and not really slow things down. Now, when we look at the CPU speed, we're at 1.37 now. We are at 21. I think that's roughly the slowdown factor of like 14 that I thought it was going to be. But the video speed is not that same slowdown factor. It's less than 10 times slower. It's more like maybe 9 times slower. Well, as I mentioned before, the ISA bus is only about 1/7 slower, went from about 7 megahertz down to 1 megahertz now. And it's the CPU slowdown that's resulting in the additional performance loss. But that's not as bad as it could be. And let's run this HD speed benchmark, which incidentally seems to be working without issue here. And let's see how much slower the hard drive is. We were getting 1943.1 K per second before, and we're now getting 193.2. We're literally getting about 1/10 the speed, which isn't half bad considering the CPU is now running at 1/14 of its original speed. Let's try the MIPS utility. Notice how the screen updated pretty quickly, even running at 1 megahertz. That screen routine obviously was writing directly to the video card memory. It wasn't using the BIOS calls, because you can see in DOS draws really slowly now, and that's because those BIOS calls are so inefficient and were really written with 4.77 megahertz in mind. But writing directly to the video card actually results in decent performance, and I can guarantee you that most good programs on the Apple II, not just basic stuff, is writing directly to the video memory as well, which means you're not dealing with BIOS calls and all that slowdown. And here are the results of the MIPS utility, and it looks like pretty much everything is just about 1/14 the speed originally. It looks like I forgot to write down one of the entries there, but we are now 0.13 at the bottom, and we were 2.0, which is around 14 times slower, which is exactly what we expected. Okay, so let's see if Check It works here. Let's see how fast this runs. It's loading, and that's obviously a lot slower. This is the hard drive LED right there, so it's blinky blinky. And oh, there it goes. Oh, you can ignore the font being messed up. That's because speed 600 alters the VGA font. Anyhow, it's working. It's slow, but it's not that slow. 1 megahertz is completely usable. I'm pretty amazed. I mean, the menus they draw pretty slowly, but overall, not terrible. Memory benchmark, 1.04 megahertz according to its timing loop. Hey, one thing I want to point out while we're waiting for this, the CPU here has a heatsink on it and is still burning hot. So even though we have a super slow clock speed going into this AMD CPU, that is obviously not why it's getting hot. It must be hot just from the power going into it, and it has nothing to do with the actual clocks going into it. I just would have thought maybe it was cooler, but nope, still totally burning hot. I can't leave my finger on that little heatsink even. All right, so here are the results. 3484 was the original result. Now we're getting 219 and 68.7 whetstones, and 4.2 is the new speed. And yeah, basically 1/14 the speed originally, which completely expected. And comparing the results for the video speed, we're getting 2716K per second on the direct video writes, and before we were getting 44,861, and the BIOS routine is 410 characters per second versus 7,165. What's interesting about the results here is that the characters per second on the BIOS routines, if I wrote this down correctly at 7,165, is a massive slowdown. That's like 17 times, maybe I'm not doing the math correctly. And then the direct video memory speeds is also like 16 times slower, from 44,861 down to 2716. So the only thing I can imagine is that Check-It's routines are highly reliant on the CPU, while the ones in Speed 600, which didn't have such a dramatic decrease in performance, are much more efficient and are not affected as much by the slowdown of the CPU clock speed. Okay, so the system was able to complete all of its benchmarks. All the results were pretty much as expected, except for Check-It video speed seemed weirdly slow. What is the system like to use? Well, there was a directory and it wasn't too bad. Now, the card I'm using right now is 128 megabytes, so it's a bit large. Old systems like this that are running at really slow speeds shouldn't have large hard drives. It take a very long time to scan the file allocation table to figure out the free space. And this slowdown here is not frozen because the light is blinking. The hard drive light is blinking right there. Unfortunately, it's just a side effect of using a large partition. If we were accessing a floppy disk with 360K or even like a 1 meg hard drive partition, it would not be as slow as this. You'll notice this phenomenon if you ever try to use like a 2 gigabyte hard drive or compact flash card on an XT, like a 4.77 megahertz machine. It just takes forever. So I think we could just ignore that slow file allocation table count up, because in the reality is if we were ever using a real machine that was this slow, we would not be using even 128 megabyte partition like this. That is just far too big for the inefficient fat scanning routine that DOS has. Now, navigating around the hard drive, how does it feel? I mean, it's really slow. I'd say that feels slower than any Apple II text mode. This is all BIOS calls. We can do mode CO40 to switch into 40 column mode here. And let's see if this is any worse or better. I don't know, it's about the same. Yeah, not any faster. Now there's a little bit more happening on text mode on a PC, because even though we're looking at black and white text here, it is in color. It does have a foreground and background color. So for every one character cell that's written to screen, there's actually another character that's written that contains the color information. So we're really writing twice as much data to screen as, say, an Apple II, which is only simply putting an 8-bit character into memory and then that's it. There's no attribute bit. Oh, and on an Apple II, you might be saying, oh, there is an attribute bit for inverse and flashing, but those attributes are not a separate byte in memory. That's just extra bits in the character cell that tell it's inverse character, for instance. Okay, so let's try a game. I am really curious to see if anything can run at any sense of a normal speed on here. Does anyone think that running software at 1 megahertz is actually going to result in any kind of playability whatsoever? I have a feeling there's going to be a big difference from one game to another on here, but let's try out Alley Cat, which I think everyone knows if you had a PC back in the day. It's a CGA game, so it's going to run in graphics mode. It was written by Sunsoft, or I forgot the name of the company, and IBM. I think it was for IBM, and it was one of their discs they released with their own software, so you could get it for your CGA 5150. It has music, and let's see if it works. Okay, Synsoft, its company name. Music is working. That loaded super quickly. It just, well, it's only 50K, but it just was there almost instantly. And it filled up the screen with graphics really quickly too. I'm gonna unplug the speaker so we don't have to keep hearing that music. But you could tell the frequency was right, the music sounded right. So even underclocking this so dramatically, no issues with that. And that would not be the case on, say, an Apple II, even if the video circuitry could work. If we ran it at 2 megahertz or 4 megahertz, the music would be super fast and not sound correct at all. And well, so far so good. So let's hit enter. We do not have a joystick hooked up. Skill level, I guess kitten. I assume that's the lowest level. Control X for exiting DOS. We'll have to just try to remember that. Okay, so I'm the little cat at the bottom here, and I really never remember how to play this game. You gotta like, oops. You got to jump around here, and I need to get up to, let's see, I need to get up on the fence and up onto the clothesline. Oh, I got hit by a telephone. What a horrible person. I'm just a little kitten. Don't hit me with a telephone. Let's see here. Jump up here. Jump up on the clothesline. Okay, there's a mouse, which knocked me off. How rude. So one thing I can say is the game seems to be playing completely without issue. I mean, I don't know how to play this game very well. Squeak. I guess I need to avoid the little mice, those little jerks, knocking me off and everything. But yes, it's working fine. That's awesome. So Control X to exit to DOS, and that worked. Sweet. Let's try Zaxxon, another CGA graphics game. I don't know if this has music, so we'll plug the speaker in. 1984. All right, enter 1 or 2 players. Joystick not attached. Okay, that's cool. It can tell there's no joystick. I don't even have a game port plugged into this thing. I'm assuming a game port would work, but I don't really know. Player 1, your turn. Okay. Now here's the animation, and you can definitely see that it's like scrolling, you know, you can see the pixels being drawn. Oh, I need to move. Oh, it moves very slowly. All right, so I can go up and down. Let's see if I can fire. All right. That's a long explosion. This game is definitely running slower than it would normally run. I've played this plenty of times on PC XTs, and I think it's faster than this. Oops, that was a fire. Yeah, it's sort of struggling to draw the pixels and everything, but it is working, and maybe with some better efficient, with some more efficient timing loops, you know, it would run faster. So let's try ramping up the speed to 3 megahertz. I'm gonna push 6 megahertz here, and okay, so that's a lot faster. I don't remember exactly how this plays on the XT, but with this running at 3 megahertz, the processor now, yeah, it's certainly animating a lot better. It's a bit faster, but you know what? It's still totally playable at that slower speed, and that's kind of cool. So that's another game that, okay, I'm gonna unplug the speaker here. So we have another game that mostly works fine at 1 megahertz. That is really kind of unexpected. I hit Control-Alt-Delete. I'm still running the CPU at 3 megahertz here, so we're getting a little bit of a boost just for that boot process, but I can slow this down. Let's go back to 2.053 megahertz. There it is. Just slowed down. System is still running, so you can change speed on the fly. Okay, the speaker's reconnected. Let's try out Spy Hunter. All right, R for RGB monitors. Make sure we are running at 1 megahertz. Yes, we are, definitely are. RGB monitor. Game loaded very quickly. Music is working. We do not have a joystick. I'll do novice. And don't remember the keys to move the car. Let's see here. Okay. Let's see, how do I move left and right? Oh, there it is. Okay, cool. All right. Well, if you're watching this at 1 speed on YouTube, what? Oh boy, graphical artifacts. When I drive the car quickly, it glitches out a little bit. So there's obviously some kind of timing loop. Maybe it's waiting for a vertical refresh or something on the CGA card. And I bet you what's happening is the CPU is no longer fast enough to catch up. Now, there's something to consider here. I'm running on a VGA card, and VGA runs at 70 hertz versus 60. So it actually is a little bit harder for these games if they take into account the vertical refresh. And that might be why this is actually glitching out. This might be a problem with this game, even on a full-speed computer with a VGA card. But if I drive slowly, let's try to knock this guy over here. Yep, that worked. Yeah, so, sorry about the flashing. If you don't like flashing, look away now. Game is absolutely playable though, other than the weird graphical artifacts, which I really think simply come from the VGA card versus a CGA card. The frame rate otherwise looks really smooth and good, and that's pretty shocking for 1 megahertz on a PC, I have to admit. Let's see, can I exit out of this? Game pause for escape. Control X. Okay, that restarted the game. I was gonna hit Control Delete. Okay, so let's try something text-based. I happen to have Planetfall on here, which I think we run with Planet FA. This is a text-based game from Infocom, Software Pirates Incorporated. I guess they changed the banner there. Do you want color? Let's just say no. And there it is, it's drawing the text. Now, I don't think this is using BIOS routines because I think the text would draw even slower here, but we can see that, I beg your pardon, let's just wait. Time passes. If I recall, you gotta wait a while. Look at floor. It's gonna tell us it sees nothing special about a clean floor. Yeah, you gotta like wait a little while. Someone's gonna come over and talk to you here, alien ambassador. Yeah, we'll just wait a little bit longer. All humans look alike. Yep, I'm not surprised. Okay, clean floor. Oops, clean the floor. Yeah, you're supposed to be washing the deck or whatnot. Ambassador is like, get out of here. So let's wait. Time passes. A massive explosion rocks the ship. Echoes from the explosion resound, deafening down the walls. The door to the port, there's an escape hatch right there. Enter the escape pod. Let's see if that works. Yep. I'm in the escape pod. You hear from close by sounds of emergency bulkheads closing. If we just wait a little bit. Yep, it closes the door and we need to say get into web. There's a webbing to hold you like it's a seatbelt kind of thing. And there we go. It is now going out of the ship through the viewport pod. You see the Feinstein dwindle as you head away. Bursts of light. Lights in the control panel blink furiously as the autopilot searches for reasonable destination. This is a very fun game, I gotta say. I really do like Infocom games. I could see how people really got sucked into these back in the day. Approaching planet, human habitable. So, yep, the ship is, or the emergency hatch. Look at the panel. Let's see if we can get it to do something more. We are now in the atmosphere, so wait a little bit longer. Yep, temperature begins to rise. Wait some more. There we go. Thrusters fire long and hard, slowing the pod's descent. And I think it's going to land. Get out of web. You are standing. Oh, I died. I didn't get out quick enough. So basically you have to get out of the web and then leave the pod, and then you're on the planet and all that kind of stuff. So yeah, that's how the game works. But you know what? This works pretty well. I would say performance seemed decent, considering I don't think this is just writing directly to the screen memory. If we type dir, I hit, darn it, I didn't do dir/b. Anyways, Planetfall's text routine seemed similar actually to DOS, so I guess it's using BIOS calls. Not surprised, it's just a very simple interpreter, the Infocom stuff. I bet you there's a more fancy one that uses direct video calls, which would be far faster on a machine like this 1 megahertz machine. And on something like an Apple II, the Infocom interpreters would not be using BIOS calls, it would just be writing directly to the screen memory, which would result in faster text display. But you know what? That didn't seem too bad at all. What else do we have to run on here? Planet X3. Let's look at something a little bit more modern. And if I just run this like this, it's actually going to run in VGA mode, which is interesting. We're going to see how 256 color mode works on such a slow machine. Kind of a configuration that you never had. Hey, look at that. Not bad. Let's go into the game here. That transition is way faster than I thought it was going to be. I thought it was going to be super slow. All right, this is a bit slow. Oh, it's actually loading. I can see the hard drive LED was blinking there. There it is. Okay, so the screen draw routine is slow, and I can't blame David Murray, for instance. I don't remember off the top of my head, but 320 by 200 at 256 colors is around 64 kilobytes or something like that. It's almost the entire main memory of something like an Apple II. And just moving around, we're having to update a big chunk of it. So I'm really not surprised that you can really see it drawing the whole screen. I think what we should do is exit out. Oh, the menu is kind of sluggish. We should exit out and we should try this game again, but in CGA mode. And instead of the normal CGA mode, we should run it in high-res CGA, which is 640 by 200. Which you can think of that mode as being much more akin to the double high-res mode on the Apple II, although I think it's easier to write to the buffer with CGA 640 by 200 than double high-res. Double high-res is really complicated to use because there's bank switching and all this kind of stuff. All we need to do is do 3 for high-res mono. I guess we'll do speaker again. I'll just unplug the speaker. So that drew pretty quickly. Transitions are quick. Let's see how quickly, it draws the screen here, moving around. There's a lot less memory to push around in the CGA mode here. Oh yeah, okay. I mean, you can still see it draw, but that is way, way faster. Not bad at all. And if you think about a game like Ultima on the Apple II, it's really running in like 280 by 192 pixels, I think, like that. So that's less than half the pixels to move around than what we're looking at here. And Apple II graphics, even though you see color on a monitor, is monochrome. There's no color information in memory. It's artifact color. And I would imagine if this game were only drawing half the screen or less, because Ultima doesn't really draw everything, it's kind of similar actually. Like the game running at this speed right here is absolutely completely playable. There is no issues whatsoever. Yep, I'm able to like bulldoze stuff without an issue. Yeah, that's pretty impressive. This game is playing really well. Now we also have as Attack of the Petsky Robots. I don't think this has a CGA mode. Has CGA Composite 16 color mode. That's probably the one we should use because that will run in that CGA 2 color mode. It's just using 640 by 200 to do the artifact color. So we do 5 and 0, and let's see how this looks. I assume it's just gonna look like an Apple II game. Yeah, it looks just like an Apple II game, but it's almost more the equivalent of double high res. So if you've ever played Apple II double high res games, let's see if we can start the game here. Okay, there it is. Not bad. Not bad at all. I mean, it's kind of what I would expect from a double high-res game running on the Apple II. Of course, if we had this plugged into an NTSC monitor, we'd have full 16 colors and everything. It's just through the VGA adapter, we're not getting that. But the game is, yeah, it's running fine. Now we have to remember this game was originally coded on the 6502 for running at 1 megahertz on the Commodore PET, and then, of course, Commodores and all the other machines, and it's been ported to everything now. But we now know that it works totally fine, at least on this 286 with 0 states running at 1 megahertz. So I also have a couple applications that are on this compact flash card. These are all things that you might run on something like an Apple II. Let's try Print Shop. This is the quintessential Apple II program here. Let's see how this works. This is gonna run in CGA low resolution mode. There it is, it came right up. And you know what? It seems to work fine. I think this is very similar to the speed of this on an Apple II. So let's just try one of these ready-made cards, make it for me. And let's preview the card and assembling the inside. If we plug in the speaker, we're gonna hear some clicks and stuff as it does the preview. All right, so I forgot how fast the preview is on the Apple. I don't even know if it could do it. I think it could do it. Pretty sure it could, but if you are really familiar with like the speed of this on an Apple II, is the preview mode similar to this? I'd say navigating around the menus feels about the same to me, but is this any worse than the Apple II? Happy birthday, Adrian. Oh, beeped at me, okay. We hit enter and it's gonna do the front of the card now. I think. Hello? Hello? I don't know what's happening. I'm assuming Maybe it's going to have like a large graphic in the front, and that slows down the processor. I don't know. Oh, there it is. Yeah. Okay. So I guess scaling the pixelated birthday cake. Hey, it's pixel art, everyone. It's pixel art. Totally ahead of its time. Anyhow, I don't have a printer hooked up, obviously, so we cannot print that, but it works. And, you know, the graphics are a direct port from the Apple II version. This is exactly the same way it looks on the Apple II. Let's exit out of here. Now I have DeskMate on here. It's from Tandy, and it lets you set up the different graphics mode. Obviously, this is a VGA card, so it would run in 640 by 480 at 16 colors. But let's give this thing a chance and run it in CGA mode, 640 by 202 color mode. So we're going to do 5, and now we type DM, I think, or no, desk. And it should go into there, and as long as you have something set up in the path, it's going to use the video driver that you specify. And there we go, a GUI. Now, if you use GEOS on the Commodore 64, for instance, it's pretty slow, and also GEOS on the Apple II is very, very sluggish. And then there's that graphical Apple desktop. It's kind of like a Macintosh looking thing. It's running in monochrome double high res, which is similar resolution to this. It's decently fast, but if we go to the menus here, I mean, the menus don't, it's not terrible. Now, DeskMate is known to be horribly slow, even on much faster machines like Turbo XTs, which is kind of what it was originally targeted. But this is not terrible. It works. It's a bit sluggish, but we have to remember this is running at 1 megahertz. So here we go in text mode here. Let's open up the word processor here. Certainly loads pretty quick. I mean, compact flash card, pretty fast. You know, it drew that text okay. So there's the cursor. Let's try to insert something. Hello. Oh, it's sluggish. There. Oh, wow. Yeah, it's very sluggish. This is a test. Oops, I mistyped that. And it's completely lagging behind. At least, oh, sorry. Let's unplug the speaker. I overtyped the buffer there. It's still typing on its own. Yeah, okay, well, that's slow. I do remember the GEOS writer word processor also being very slow, but I'd love to hear comments from people who use that a lot and could tell me if the performance here is similar to that 1 megahertz performance on the Apple II or the Commodores and stuff that ran that utility. Yeah, interesting. So we're gonna exit out of this, save changes, no. We can imagine if we ran this in VGA mode, it would just be a lot slower because we have to push so many more pixels around, 640 by 480, and we have color then and stuff like that. And this is a bit better of a comparison. Now, most word processors on the PC back in the day were text mode, like WordPerfect here. Let's try to load a file. I think that's the one we're just editing, dmvid.doc, and let's load this into WordPerfect here. I barely can remember how to use WordPerfect. And with WordPerfect, if you don't have the little keyboard template thing, good luck. I just remember how to exit. I think it's like F7. So let's see if this works. But we can at least see if it's a little bit faster at editing text or inserting text. It's loading. Oh, yep. Okay, there we go. It was very slow. I wouldn't be surprised if this is doing the fat calculation for disk space stuff though. All right, there it is. So let's see about inserting. Inserting text. Wow, yeah, this is much better and much faster now. I mean, this is a huge difference. It's still a little bit slow when it comes to, let's see about scrolling. Oh, scrolling is fast. So it's using a pretty quick routine to actually scroll the screen. I doubt it's a BIOS routine. It's probably direct. It's doing it directly, and then it just has to draw the line of text in the bottom. Not terrible. So this is completely usable. And I remember the way AppleWorks was, for instance, on the Apple II, and it, you know, was pretty good experience, but again, it's running in black and white. It doesn't have the color like this has. So there's, you know, it's not direct apples to apples comparison, but this is not bad for 1 megahertz. Really not bad. Okay, F7 to exit, save document. No, exit, yes. Right, I remember, amazing. WordPerfect 5.0, even though it's version 5, it doesn't have a menu. It has no menu. You have to use the little thing above your keyboard so you know what all the F keys are. It seems wild to me. They wouldn't have just designed in, you know, a help screen or whatever. Maybe it does have a help screen to be honest, but something to just guide you through it. People have noticed on my SD card, I have a BBC Basic directory, and they're like, what's that all about? Yes, there's a port of BBC Basic to the PC, and it's old. It's not even something that's new. Notice the dates on these files. Well, some of them were 86. Yeah, this was done a long time ago, and I just don't think people really knew about it, and it does absolutely work. So let's see, there's a little program there, sign.bbc. So there we are. Looks like this one was ported in 2000, but this is a much later version. I think there were earlier versions that were done as well. But yeah, it totally exists, and it's 100% BBC Basic compatible. So let's load the Sine program here, and I think it's going to draw some graphics. There it goes. Now, I couldn't tell you how fast this would be on the real BBC, this exact example, but we have to remember that it would be running at double the speed, so let's do that. So I run it at 4 megahertz, so the CPU is running at 2 megahertz now. And yep, so let's run that again. And now we're running at the same speed as the BBC, and I don't know, someone tell me if this is the same speed as the one on the BBC running at 2 megahertz. I would be very curious. Now, BBC Basic generally is very efficient compared to other versions of Basic. For whatever reason, running on the same system as, say, the Microsoft Basic, this actually is more capable and faster. So it's kind of a win-win situation. Now, I have a fractal benchmark that I've used to actually sort of benchmark various versions of Basic. And let's run this and see how fast this goes. And you can run this on any of your systems. And I have a little spreadsheet, which I'll put a link to in the description below, so you can see how fast this runs on all sorts of different systems. But yeah, oh no, this is not a good test. We're running this at the wrong speed here. 2.053 megahertz. Okay, there we go. Now we're running at the correct speed. Oh, yeah, that's a lot slower, half the speed, I guess. And let's see how long this takes to run. Okay, it completed, and it finished in 524 seconds. So it's relatively slow being BBC Basic, but you'll notice here that while it's slower than the Apple II GS at 1 megahertz or the Apple IIe at 1 megahertz, which are 489 each, and that's running AppleSoft Basic, it's still not super terrible. The Commodore 64 running obviously Microsoft Commodore Basic, running in 80 columns mode, because this test is really designed for machines with 80 columns, because, you know, it would be scrolling more than it needs to if it wasn't 80 columns. That runs in 542 seconds, actually a little bit slower, and that's on the Ultimate 64, running in the stock clock speed. Now, one thing we can see for sure, though, is that the BBC Micro itself runs in 2 megahertz in the 6502 in 233 seconds, this exact same benchmark. So I think there's more going on here besides the half the clock speed, because that would be about 460, and we are getting, you know, far worse than that on this machine at 524. So I think that the BBC Basic that's written for the PC maybe is just not as efficient as the one on the 6502. I don't know how good the port is, but it's just kind of curious. From this testing, I think I've established a 1 megahertz PC, albeit a 286 with 16-bit RAM and all that stuff, is not terribly slow and is totally usable. Going into this video, I really didn't have an idea of how usable the system would be at these slow clock speeds. I kind of figured it would be so slow that it would be really difficult to do anything. But to be honest, this system as it sits right now is perfectly usable, at least for really old programs that, you know, don't take advantage of the speed. I wouldn't try running Windows for Workgroups 3.1.1 on this system. It probably would be too slow to use reliably. But to be honest, if you looked at people who were trying to play Doom on machines that were way slower than they should have been, like 36SX machines, and people played that game and totally enjoyed it, you know, low resolution into small window in the middle, it means that back in the day, we sort of put up with a lot with these computers. Not everyone could afford a state-of-the-art machine, and sometimes you wanted to play games on something that was designed for something faster, and you just put up with the slow speeds. And running games like Zaxxon and Alley Cat and Planet X3 and Petsky Robots all resulted in completely playable games, and even programs like WordPerfect and stuff was totally fine. Deskmate might have been a bit of a push, but to be honest, every time I've used Deskmate, even on a Tandy, it's super slow there too. So I think probably would be fine as well, especially in that low bit depth CGA mode, which is just pushing less pixels. Now, one thing I'm still curious about with this whole setup is how slow can I run this machine? I haven't gone below 1.0 megahertz really. Can we run this thing in the kilohertz range? what would that be like? I think if the thing still is able to run at that slow speed, it's going to start to become incredibly miserable of an experience. Okay, so let's turn on the oscilloscope. It seems to have gone to sleep at some point that I didn't really notice. Yes, it's running at a fast speed right now because it's quicker to boot up that way. Let's go to 1.0 megahertz here. And let's see if the system is still working. No, it froze. Okay, so that big of a jump, it was not happy with that. Let's go to 8 megahertz here. Yep, system is still frozen. So let's do the old typey thing again, and I'm going to start turning this down, and you can see on the oscilloscope here, see how it's widening. Let's see if we can get back down to where we were, where the system has crashed. Oh no, the system has crashed. And that's at 1 megahertz. So 500 kilohertz, it's not working. This could well be a problem with the keyboard controller again, kind of similar to what we were having before. So let's put this thing back up to 8 megahertz here, reboot the system. One way to test if the whole motherboard's crashing or the CPU, or it's just the keyboard controller, is to run speed 600, because it's a real-time speed test. And with the speaker hooked up, we're gonna hear the ticking coming out of it. Maybe. There we go. And now let's lower this down here. Five, 4, 3, 2. That is funny how slow it is. Okay, so let's switch over to the fractional megahertz. Okay, we're at 1.6 where the keyboard stopped working. The computer's not crashed, obviously. It's still running. It still works. So the CPU is running at 646 kilohertz right now. And it is absolutely executing code. Clearly the problem is the keyboard controller. It does not like running at this slow clock speed. So that's why we can't type anything. So unfortunately the system is not usable. But the system is still running. Let's keep going lower here. It's still going. Still going. Oh man. We are at exactly 500 kilohertz right now, so 286 at 500 kilohertz. How low can we go? It has not crashed. It has not crashed yet. Oh, I mean, the speaker is barely able to produce the sound anymore. We're at 400 kilohertz CPU speed now. Wait, what happened? Okay, so it's at 350 kilohertz, but it sounded like the beeping out of the speaker went up in frequency. I'm going to go back to 400. Yeah, we're at 400 kilohertz, and it did go down. Let's go down again. So we're at 350 kilohertz. Yeah, the beeping went up, the frequency. That's weird. Let's keep going down. 299.4 kilohertz. And the system is still running. That is the CPU speed right now, 300 kilohertz. And it's executing code, all right. Let's keep going down. It's gonna crash eventually, I assume. 250 kilohertz. It's still freaking working. Updating the video, the timing loop is working, the VGA card is working. I mean, 0.23. Let's go down one more. Let's see here. We're now at 200 kilohertz. I'm shocked. Okay, so we're not getting a sound anymore. I wonder if it's using the interval timer. I think it is, because when I change the CPU speed while it's making the beep, it doesn't change frequency, so it's using the interval timer. I think it's reached the bottom of the interval timer's range. It has a certain range, but is it updating the screen? Because we would see it kind of refresh where it says CPU there. Oh, it just, yeah, it's not crashed. This machine is currently running at 200 kilohertz. Let's keep going down. Got to change the scale on the scope. 150 kilohertz. I mean, this is kind of getting silly, isn't it, here? But there it is. It just updated the screen. So I guess there's no lower minimum that I can tell, at least. I mean, if we could type, it would be really cool to see how slow this would be, obviously. I suppose what we can do is I'm at 300 kilohertz on here. Let's go back to, well, first we'll go back to 3 megahertz, see if we can get the system. Okay, there we go. Let's exit out of here. The keyboard is still working. What I want to do is enter a game like Planet X3, which has some animation that's happening on screen, and then we'll just ramp right back down to the 150 kilohertz. I meant we're going to go to Petsky Robots because that has robots and stuff that are moving around on screen, and we're going to do CGA composite color again, just like we were doing before. I'll just skip the sound altogether. We're currently running the CPU at about 1.5 megahertz right now. So let's enter the game and get over to the part of the level that has some robots moving around. so we can see some animation. Okay, so there's a robot. We're now running the CPU at 100 kilohertz. Did it freeze? Nope. You can see the draw routine. Interesting. I think it draws in the new location first and then erases the old one, but it's so slow right now that it doesn't seem to be moving at all. Oh, there we go. Very interesting. Let's ramp it down. So we're at 50 kilohertz right now. The CPU is running at 50 kilohertz, 50. Will the robot move? I've been waiting here for a little while and it hasn't moved. So we may have reached the limit and the system may actually be crashed. I'll know if I ramp up the speed and it starts moving again. That means the system didn't crash. It just got so slow that it couldn't possibly work. Still hasn't moved. Let's see what the ISA clock speed is. 49.8 kilohertz. Here we go. Let's ramp it up. Okay, yeah. The computer has crashed. Yep, because I'm at 2 point whatever megahertz now, which we know it runs fine at. And the system is totally dead. So 50 kilohertz, too slow for the AMD 286 and the chipset or whatever to work. Completely understandable. You have to remember that internal to these chips, like the chipset and the CPU, there are those registers and they're like RAM and they need to be refreshed. And I'm quite sure, at least on the chipset, but probably on this CPU as well, it's not designed to run at 0 hertz. And therefore, you got to keep some clock going to keep those registers refreshed in there. Otherwise, the values decay and then the system just crashes, which is exactly what we just saw. So there we go. I think that's it for this video. I really pushed this motherboard to the limit, both at the top. We know 28 point whatever is about as fast as it can go on the high end. And obviously somewhere around 100 kilohertz is the low end. 100 worked, 50 wasn't working. So somewhere around there, the system becomes so unstable and it crashes. And then for the keyboard controller that's on here, it was working at CPU speed of 1 megahertz, but around a CPU speed of 750 kilohertz or so, whatever clock signal was going into the keyboard controller was too slow and the keyboard stopped working, which means you can't really use the computer anymore. So even though this is a very useless video and no one would ever really want to do this to their computer and run it this way, I thought it was a fun experiment just to see how far we could push this thing. And if at 1 megahertz, the same speed as my Apple IIc sitting right here, would that result in an IBM PC that was actually usable and you could run games and software on? And the answer is yes. It totally works fine at 1 megahertz. And to be honest, those games were pretty playable, and I've gone ahead and I played some other games on here as well at 1 megahertz, like Load Runner and other stuff, and they work just fine. They're slow, and I'd say they seem to play a little faster on the Apple II, but they're not unplayable by any means, and the system is totally usable, even at 1 megahertz, just not at 100 kilohertz. That is way too slow. So if you liked this video, I'd appreciate a thumbs up. If you didn't, you know what to do. If you have any comments about this whole experience, I know I've sort of put a lot of questions out there to people about this whole thing. Comment down below about it. And then huge thanks to my patrons. Names are up the screen over here. They make it possible to do this full time. And that's really that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.